On the limestone plateau of Baalbek in present-day Lebanon, vast carved blocks still form part of a monumental platform beneath the Roman temple of Jupiter. Nearby quarries preserve unfinished monoliths still anchored to bedrock, their surfaces marked by precise cutting lines that stop abruptly mid-process. The scale and precision of the stonework leave a landscape that feels suspended at the point where construction and abandonment meet. What unfolds before you is evidence that does not settle into a single explanation, where quarry marks, transport traces and foundation stones point in different directions rather than forming one clear account. As each layer is examined, the site reveals a pattern of skill and interruption that resists familiar construction logic, leaving behind a structure that can be seen in full but not fully explained. The stone that was too heavy to move. The hills surrounding Baalbek do not immediately resemble the setting of one of history's greatest engineering mysteries. Dry grass moves across broken limestone ridges, the air carries dust from the Bekaa Valley, and fragments of ruined columns still rise from the earth like the remains of a forgotten empire. For centuries, travellers approaching the ancient site focused their attention on the towering Roman temples standing above the landscape, yet the most unsettling discovery was never inside the sanctuary itself. It rested quietly in the ground beyond the temple walls, half buried in a quarry where the stone beneath the surface appears to have been opened by human hands on a scale that still feels deeply unnatural. Even before measurements were completed, the object forced archaeologists and engineers into an uncomfortable position, because the farther they studied it, the more difficult it became to explain how any ancient civilization could have intended to move it at all. Long before modern surveys reached the quarry, local tradition surrounding Baalbek had already drifted into legend. Medieval Arab writers associated the site with giants and ancient kings, while later European travellers often described the ruins with disbelief, struggling to reconcile the scale of the stonework with the accepted limits of ancient construction. Some attributed the platform to biblical figures, others imagined lost civilizations, and many simply admitted that they could not understand what they were seeing. Those stories survived partly because Baalbek does not appear gradual or ordinary when viewed in person. The foundations beneath the Roman temple complex are built from stones so large that even modern industrial equipment would approach them with caution, and hidden nearby lay something even more disturbing, a monolith abandoned before it ever reached the temple. The object became widely known as the Stone of the Pregnant Woman, a name connected to local folklore that developed long after the quarry itself fell silent. In Arabic, it is called Hajar el-Hibla, though the meaning behind the title remains debated. Some traditions claimed a pregnant woman possessed secret knowledge capable of moving the stone, while others suggested the name emerged from stories connected to fertility rituals in the region. Whatever the origin, the monolith itself is real, and its dimensions are staggering even by modern standards. The stone measures roughly 20 meters in length, more than 4 meters in height, and over 4 meters in width. Estimates of its weight have varied for decades, but many calculations place it at approximately 1,000 tons, making it one of the largest known stones ever cut by human beings. What makes the monolith especially unsettling is not simply its size, but the evidence surrounding it. The stone was not naturally separated from the bedrock through geological fracture. Clear-cut lines remain visible along its sides, showing where workers carved deep trenches around the block in preparation for extraction. Marks left on the limestone reveal prolonged and organised labour, suggesting the quarrying process followed deliberate planning rather than experimentation. The stone was partially detached, angled slightly upward from the quarry floor and then abandoned before completion. That single detail continues to dominate discussions among archaeologists and engineers alike, because it demonstrates that the builders not only imagined moving such a massive object, but had progressed far enough into the operation to believe it was achievable. For generations, many researchers assumed the Stone of the Pregnant Woman represented the upper limit of ancient stoneworking. That assumption collapsed in 2014 when archaeological excavations conducted by the German Archaeological Institute and the Lebanese Directorate General of Antiquities uncovered another enormous monolith buried nearby beneath layers of soil and debris. The newly revealed stone, now often referred to as the Stone of the South, exceeded even the dimensions of the earlier monolith. Measurements indicated a length approaching 20 meters, a width nearing 6 meters, and an estimated weight potentially exceeding 1,600 tons. The discovery transformed the quarry from an archaeological curiosity into one of the most difficult engineering sites in the ancient world to explain. The reaction among researchers was cautious but unmistakable. Stones of that scale are not merely difficult to transport, they exist near the practical limits of what many modern heavy lifting systems can safely manage. Even contemporary crawler cranes used in industrial megaprojects operate under highly controlled conditions involving stabilised ground, advanced hydraulic systems, reinforced transport routes, and precision-engineered lifting points. The Baalbek stones existed in an ancient landscape with none of those advantages. The quarry floor slopes unevenly, the route toward the temple platform rises gradually uphill, and the distance between the quarry and the complex spans hundreds of metres. Every physical condition surrounding the site appears to work against the possibility that the stones could have been transported successfully. Yet several enormous blocks did reach the temple. That contradiction sits at the centre of the Baalbek mystery. The unfinished stones in the quarry prove the builders attempted to extract colossal monoliths, while the surviving temple platform confirms that similarly massive stones were ultimately positioned with extraordinary precision. The famous trilithon blocks incorporated into the retaining wall of the Temple of Jupiter each weigh an estimated 800 tons or more, and they remain suspended several metres above ground level within the structure itself. Even stripped of decoration and partially damaged by earthquakes, the platform still communicates an unsettling sense of permanence. The stones appear less assembled than imposed upon the landscape, as though entire sections of the hillside had been reshaped into architecture. Roman engineers are often credited with the visible temple complex constructed at Baalbek during the early imperial period, particularly under emperors such as Nero and Antoninus Pius, when the sanctuary reached its monumental height. The Temple of Jupiter eventually became one of the largest religious structures in the Roman world, surrounded by immense columns cut from Egyptian granite and local limestone. Yet the deeper foundation beneath the Roman additions has continued to generate debate, because portions of the lower platform differ significantly in scale from conventional Roman masonry. Some archaeologists maintain the Romans themselves completed the megalithic construction using methods now poorly understood, while others argue that at least part of the platform may predate Roman occupation entirely. The quarry monoliths intensified that debate because they reveal ambitions extending beyond ordinary architectural requirements. A 100-ton stone can already serve as a monumental foundation block. Even several 100-ton stones surpass the needs of most ancient construction. But stones exceeding 1,000 tons move into a different category entirely, one where the engineering challenge becomes so extreme that questions naturally emerge about why such dimensions were considered necessary in the first place. The quarry does not show evidence of moderation or gradual scaling. Instead, it suggests a workforce repeatedly attempting to produce some of the largest building blocks in human history. Researchers studying the quarry have noted that the limestone itself may have influenced those decisions. The stone extracted around Baalbek is relatively dense but workable, allowing skilled labourers to carve large blocks with remarkable precision. Ancient quarry workers likely used iron tools, wedges, and systematic trenching techniques to isolate sections of bedrock before gradually separating them from the ground beneath. Similar quarrying methods are documented across the Roman world, but Baalbek expanded the scale to an almost incomprehensible degree. Each successful extraction would have required enormous coordination, careful measurement, and precise control over fractures within the stone. A single major crack could ruin months of labour instantly. That possibility may explain why some of the largest monoliths remained unfinished. Archaeologists examining the buried stones identified structural imperfections and natural flaws running through portions of the limestone. One theory suggests workers discovered these weaknesses too late in the extraction process, forcing them to abandon the stones before transport began. Another possibility is that shifting political priorities or construction plans interrupted the project entirely. Yet even if those explanations are correct, they leave the larger mystery unresolved because at least some stones of nearly comparable size were successfully moved into place elsewhere within the complex. Modern experiments attempting to recreate ancient transport systems have offered only partial answers. Historians have proposed combinations of wooden rollers, sledges, ropes, lubrication systems, compacted earth ramps, and massive labour forces numbering in the thousands. Some calculations suggest that coordinated teams pulling in rhythm across prepared surfaces might have generated enough force to move extraordinary loads slowly uphill. But these theories remain difficult to test realistically, because almost no modern research institution possesses both the resources and the willingness to attempt transporting a 1,000-ton monolith using reconstructed ancient methods. The risks alone would be enormous. The quarry itself preserves the silence surrounding those unanswered questions. The unfinished stones remain embedded where ancient workers left them, still connected to the earth after centuries of earthquakes, invasions, and political collapse. Empires disappeared around them, religions transformed, entire civilizations rose and fell across the Mediterranean world, while the monoliths continued to rest inside the limestone ridge, untouched except by wind and dust. Their unfinished state creates the strange impression of interrupted labour, as though the builders intended to return but never did. Today, visitors walking through the quarry often struggle to judge the true scale of the stones until another person enters the frame beside them. Human figures immediately appear unnaturally small against the cut surfaces. Tool marks stretch across the limestone like shallow scars, and the trenches surrounding the monoliths descend into the bedrock with geometric precision that still feels startlingly modern. The closer the quarry is examined, the less it resembles a primitive construction site, and the more it resembles evidence of an engineering operation operating at the absolute edge of physical possibility. And beneath the hills surrounding Baalbek, the quarry itself still holds the first clues to how such impossible stones were ever carved from the earth at all. Beneath Baalbek lies one of the largest ancient quarries ever found. Below the unfinished monoliths, the limestone hillside begins revealing signs of an operation far larger than the abandoned stones alone first suggest. The quarry below Baalbek does not resemble the chaotic remains of ancient labour scattered randomly across a mountainside. Instead, the terrain carries the unmistakable appearance of deliberate organisation, where entire sections of bedrock were methodically opened, measured, and cut apart over generations of work that permanently altered the shape of the hill itself. Standing near the excavation area, it becomes difficult to separate the natural landscape from the marks left behind by human hands, because the stone surrounding the quarry no longer feels untouched or geological. Vast surfaces have been flattened, trenches descend into the limestone at unnatural angles, and exposed rock faces preserve scars that still appear sharp despite centuries of erosion. The deeper archaeologists examined the quarry, the clearer it became that the abandoned monoliths represented only the visible remains of something much larger, an industrial-scale operation capable of producing stones unlike almost anything else in the ancient world. Across the exposed quarry floor, long trenches carved into the bedrock still follow deliberate lines that remain visible after thousands of years of erosion and seismic damage. Some channels run parallel to one another with remarkable consistency, while others curve carefully around partially isolated blocks that were never fully detached from the mountain beneath them. The trenches themselves reveal the logic of the quarrying process because ancient workers did not simply strike the stone randomly until sections broke loose. Instead, they appear to have followed a controlled sequence of excavation, gradually cutting deep corridors around selected portions of limestone until enormous blocks remained suspended above the quarry floor on narrow supports of untouched rock. In several places, the cuts descend with such precision that the stone begins to resemble architecture long before it ever leaves the ground. Nothing about the excavation appears improvised once the cut channels surrounding the buried blocks start emerging from the stone with almost geometric consistency. Archaeologists studying the site observed that the quarry workers understood the limestone in extraordinary detail, selecting areas where the bedrock remained relatively dense and structurally stable while avoiding sections fractured by natural weaknesses. This required more than brute force alone. The builders needed experience capable of recognizing how the stone would respond once pressure began shifting during extraction. A single miscalculation could split a monolith apart after months of labour, rendering the entire operation useless. The immense unfinished blocks still resting in the quarry preserve that tension permanently because they remain frozen at different stages of separation, capturing moments where the work either stopped intentionally or failed before completion. Early archaeologists working around Baalbek quickly realised that the quarry itself represented one of the most important parts of the entire mystery, rather than merely the source of construction material. The Roman temples towering above the city naturally attracted immediate attention because of their immense columns and surviving walls, yet the quarry exposed something more revealing than the finished structures ever could. Buildings often conceal the methods used to create them beneath decoration and reconstruction, But quarries preserve the process. Every trench, discarded fragment, and unfinished cut records physical decisions made by workers thousands of years ago. At Baalbek, those traces suggest planning on a scale that continues to challenge assumptions about ancient engineering capabilities. Several narrow extraction corridors descending into the limestone preserve the exact stages ancient workers followed while attempting to separate enormous blocks from the mountain beneath them. The process likely began with careful marking across the bedrock surface before teams armed with iron tools started cutting channels around the chosen stone. Archaeologists believe workers used picks, chisels and wedges to deepen the trenches gradually, removing debris layer by layer, while maintaining control over the integrity of the block itself. In some ancient quarries across the Mediterranean, wooden wedges soaked in water were inserted into narrow cracks, so expansion pressure could help detach stone from the bedrock. Similar techniques may have been employed at Baalbek, although the unprecedented scale of the monoliths pushed every stage of the process into territory rarely seen elsewhere in the Roman world. Iron tools almost certainly played a central role in the quarrying process, yet the surviving marks left across the stone suggest a level of coordination that extended far beyond ordinary labour. Tool impressions preserved along the trench walls reveal repeated strikes, delivered in systematic patterns rather than scattered blows made without planning. The cuts maintain relatively consistent depth across long sections of limestone, implying organised teams worked according to shared measurements and extraction strategies. This becomes especially unsettling when considering the dimensions of the largest unfinished monoliths. A stone weighing more than 1,000 tons could not simply be adjusted easily once mistakes occurred. Every stage of extraction demanded careful control from the beginning, because correcting major errors later would have been nearly impossible. Scattered fragments surrounding the larger cuts reveal that workers repeatedly tested the limestone before committing to the dangerous process of isolating massive monoliths. Smaller discarded sections appear throughout the quarry, suggesting that teams removed unstable material or abandoned flawed extraction attempts before focusing on larger blocks. Some archaeologists believe the quarry expanded gradually as workers discovered which areas of the hillside contained the most suitable stone, while others argue the operation may have followed a broader architectural plan from the beginning. Either possibility points toward remarkable logistical organisation, because quarrying on this scale required more than skilled stonecutters alone. Labourers needed food, water, tools, supervision, transportation systems, and carefully coordinated schedules capable of sustaining prolonged activity across difficult terrain. Unlike many ancient quarries that expanded gradually through smaller removals, the excavation at Baalbek appears to have been designed from the beginning around extraordinary scale. The dimensions of the unfinished monoliths do not suggest experimentation leading slowly toward larger ambitions. Instead, the quarry reveals repeated attempts to isolate blocks already approaching the upper limits of what ancient engineering could realistically transport. This detail continues to disturb researchers because it implies the builders operated with confidence rather than uncertainty. The workers cutting those trenches behaved as though stones weighing hundreds or even thousands of tons belonged within the expected range of construction possibilities. Deep beneath the modern surface, excavations conducted during the 21st century exposed additional buried sections of the quarry that had remained hidden for centuries beneath compacted debris. In 2014, archaeologists uncovered another enormous unfinished block beneath layers of soil near the stone of the pregnant woman, revealing a monolith even larger than many earlier estimates associated with the site. The discovery reinforced suspicions that the visible quarry represents only part of a much broader extraction complex extending farther beneath the surrounding hills. Each new excavation has gradually expanded the known scale of the operation, while simultaneously increasing the difficulty of explaining it. Researchers studying the unfinished stones noticed that some portions of the limestone contained natural fractures capable of destroying months of labour without warning. Cracks running invisibly through the bedrock may explain why several monoliths remained abandoned before transport began. Once a flaw became visible, continuing the extraction would have risked catastrophic collapse during movement. Yet even this explanation creates another layer of mystery, because the workers clearly possessed enough experience to recognise these dangers while still pursuing blocks of astonishing size. The quarry reflects repeated attempts to balance ambition against material limitations, as though the builders constantly operated near the edge of failure. Evidence preserved inside the quarry suggests that hundreds of labourers may have worked simultaneously across different extraction zones during periods of major construction. Coordinating such activity required extensive planning, because quarrying did not occur in isolation from the temple complex above. Roads or transport pathways needed preparation, tools required continual replacement, and extracted stone had to move through carefully managed stages before construction crews could position it inside the sanctuary. Ancient Roman engineering projects often relied on disciplined labour systems involving soldiers, local workers, slaves, and specialised craftsmen. But Baalbek pushed those systems toward an almost unimaginable scale. Few ancient industrial sites leave behind such direct physical evidence of human effort because the quarry still preserves the precise locations where workers stopped cutting and never returned. In many historical construction zones, later rebuilding erased earlier phases of labour beneath new architecture or urban expansion. Baalbek's quarry remained exposed instead, allowing modern researchers to examine unfinished activity exactly where it ended centuries ago. The effect is strangely intimate despite the monumental scale. Every abandoned trench suggests interrupted movement, every partially detached block preserves the final stage of an operation, suspended indefinitely between extraction and transport. Even the silence surrounding the excavation site contributes to the unease many visitors describe after realizing the entire hillside was systematically reshaped by hand. Wind moves through the quarry where thousands of workers once cut stone from the earth with iron tools and coordinated labour, yet almost nothing remains of the people themselves. No machinery survived, no written technical manuals describing the full process were ever recovered. The builders disappeared while the physical evidence of their work remained embedded permanently in the mountain. That absence has allowed speculation surrounding Baalbek to expand for centuries, especially because the quarry forces modern observers to confront achievements that feel strangely disconnected from conventional expectations of the ancient world. Far above the quarry floor, the massive temple platform continued waiting for stones that somehow had to be moved uphill across difficult terrain before construction could even begin. This is where the quarry stops providing clear answers. Archaeologists can reconstruct portions of the extraction process from surviving trenches and tool marks, but the next stage remains far more difficult to explain convincingly. The slope separating the quarry from the temple rises gradually toward the sanctuary, creating a route where gravity itself worked against transport efforts. Even today, moving a 1,000-ton object across unstable ground would demand extraordinary preparation using modern machinery, specifically designed for heavy industrial operations. By the end of the Roman period, the quarry had already become inseparable from the larger mystery surrounding Baalbek, because the extraction methods alone seemed to exceed normal expectations of ancient engineering. The abandoned stones demonstrated that the builders possessed the knowledge, labour organisation, and confidence necessary to reshape entire sections of a mountainside in pursuit of colossal monoliths. Yet the quarry also revealed limits. Some blocks remained unfinished, others never left the ground. The site preserves evidence of both astonishing capability and unresolved failure at the same time. Yet the deeper shock waited beyond the quarry itself, inside the platform where several colossal stones had somehow already been raised into position. The trilithon blocks changed everything archaeologists thought they knew. Rising above the quarry where unfinished monoliths remain trapped in the limestone, the western platform of Baalbek introduces an even greater contradiction. The abandoned stones below already force uncomfortable questions about the limits of ancient engineering, but the platform towering above them transforms the mystery into something far more difficult to explain. At the quarry, the stones still belong to the mountain. Inside the retaining wall of the Temple of Jupiter, they no longer do. Somehow, several colossal blocks were detached from the hillside, moved across uneven terrain, and raised into a position high above the surrounding ground, where they continue resting more than 2,000 years later. The closer visitors approach the platform itself, the more unnatural the structure begins to feel, because the scale of the masonry does not resemble ordinary construction. It resembles mass imposed against gravity. High within the retaining wall beneath the Temple of Jupiter, 3 colossal stones continue resting in a position that should have been almost impossible to achieve in the ancient world. Together, these blocks became known as the trilithon, a term derived from the Greek words meaning 3 stones. Although partially hidden within the broader structure of the temple platform, the blocks dominate the western side of the sanctuary, with an overwhelming physical presence that becomes fully apparent only when viewed from below. Their surfaces appear almost deceptively smooth at a distance, but standing near the wall reveals dimensions so large that the mind struggles to process them accurately. The stones are not rough boulders stacked carelessly into place. They were shaped deliberately, aligned precisely, and integrated into the retaining wall with a level of control that continues to disturb engineers and archaeologists alike. Standing beside the platform alters the scale of the mystery immediately because the human eye struggles to process the dimensions of the masonry correctly. Tourists walking along the base of the retaining wall often appear unnaturally small against the stones, reduced almost to the scale of shadows moving beside a cliff face. Photographs rarely capture the effect properly because there are few familiar objects capable of communicating the true size of the blocks. Each stone stretches across nearly 19 meters in length, while its estimated weight approaches or exceeds 800 tons. Those measurements place the trilithon among the heaviest stones ever successfully incorporated into architecture anywhere in the world. Unlike isolated monoliths standing vertically as monuments, these blocks were positioned horizontally inside a structural platform, requiring not only transportation, but precise placement within an already evolving construction system. Unlike the unfinished blocks left behind in the quarry below, the trilithon stones were not merely extracted from the earth, but somehow transported and raised several meters into the structure itself. That distinction changes the engineering problem completely. Quarrying massive stone already requires extraordinary labour coordination, but lifting and positioning stones of such weight introduces an entirely different set of physical challenges involving balance, pressure distribution, structural stability, and controlled movement under immense stress. The retaining wall itself rises above lower courses of stone, meaning the builders could not simply drag the blocks across flat ground into their final positions. At some stage of construction, the stones had to be elevated carefully while preventing catastrophic collapse or uncontrolled shifting that could destroy months or even years of labour instantly. Each of the 3 blocks measures roughly 19 meters in length and weighs an estimated 800 tons or more, placing them among the heaviest stones ever successfully incorporated into architecture. Modern estimates vary slightly depending on density calculations and surviving measurements, but even conservative figures place the stones far beyond the weight range associated with most ancient construction projects. By comparison, many of the largest blocks used in Egyptian pyramids weigh only a fraction of the trilithon stones. Roman builders certainly transported enormous materials across the empire, including granite columns shipped from Egypt and heavy foundation stones used in harbours and temples. Yet Baalbek exceeds normal Roman scale so dramatically that researchers continue debating whether the project represented an extreme expansion of known techniques or evidence of something more unusual. Gravity becomes impossible to ignore once the placement of the trilithon is examined from beneath the retaining wall, where the stones loom silently above the lower courses. Every visible detail intensifies the contradiction. The blocks were not stacked loosely with wide gaps or irregular balancing points. Instead, they fit tightly together within the wall with remarkable consistency across their enormous surfaces. Even after centuries of earthquakes, invasions, dismantling and structural collapse across the rest of the sanctuary, the trilithon remains locked into position with unsettling stability. The stones create the impression that they belong naturally within the hillside itself, as though the wall had been carved from continuous bedrock rather than assembled block by block through human labour. Roman engineers constructed monumental projects throughout the Mediterranean world, yet almost no surviving structure approaches the same combination of mass, elevation, and precision found at Baalbek. The Romans possessed advanced knowledge of cranes, pulleys, treadwheel lifting systems, and large-scale construction logistics. Ancient authors such as Vitruvius described engineering methods capable of raising substantial weights using coordinated manpower and mechanical advantage. Archaeological evidence from ports, amphitheatres, and temples confirms the Romans routinely handled blocks weighing dozens of tons and occasionally much more. But Baalbek forces those known capabilities into uncomfortable territory because the trilithon stones exceed the weight of most documented Roman lifting operations by an enormous margin. Carefully fitted joints running between the stones reveal that the builders maintained extraordinary control over alignment despite the overwhelming size of the blocks themselves. The precision becomes even more striking when viewed against the realities of ancient transportation. Moving heavy objects across rough terrain naturally introduces instability, minor shifts, and surface damage. Raising them into position increases those risks dramatically. Yet the trilithon stones align with one another closely enough that the retaining wall appears intentional and measured rather than improvised. Researchers studying the joints observed that the blocks distribute pressure efficiently across their surfaces, contributing to the structure's long-term stability during seismic activity that devastated surrounding sections of the temple complex. Ancient lifting systems documented elsewhere in the Roman Empire were capable of raising heavy materials, but the scale involved at Baalbek pushes many known methods beyond their accepted limits. Historians have proposed enormous earthen ramps, combinations of rollers and sledges, or gradual lifting systems involving stacked supports beneath the stones as they advanced upward incrementally. Some theories suggest the builders relied less on vertical lifting and more on controlled horizontal movement along elevated embankments that were later dismantled after construction. Each explanation addresses part of the problem while leaving other questions unresolved. The immense weight of the stones would have generated extraordinary ground pressure during transport, particularly on uneven terrain surrounding the sanctuary. Several modern engineering studies attempting to calculate the movement of the trilithon reached the same troubling conclusion that transport alone would have required immense coordination and near-perfect stability. A single uncontrolled shift could crack the limestone, destabilize the transport system, or kill large numbers of workers instantly. The stones also needed to remain structurally intact throughout the process, because even minor fractures could compromise their usefulness inside the retaining wall. Researchers comparing Baalbek to later heavy transport operations often note that modern industrial projects depend heavily on steel reinforcement, hydraulic systems, engineered road surfaces, and machine precision unavailable in antiquity. The trilithon therefore occupies a strange position historically, where the accomplishment feels simultaneously undeniable and almost incompatible with the technological world usually associated with it. Narrow spaces separating the blocks from surrounding masonry suggest that the stones were positioned with remarkable accuracy rather than simply dragged into approximate alignment. This detail matters because the trilithon was not decorative. The blocks formed part of a massive retaining platform supporting the sanctuary above, meaning structural reliability was essential. Builders working at Baalbek appear to have understood how enormous weight could create long-term stability when distributed correctly through large interconnected stones. In some respects, the platform behaves less like conventional masonry and more like engineered geology, where the distinction between architecture and landscape begins to disappear. Centuries of earthquakes that shattered columns and damaged much of the temple complex failed to dislodge the trilithon from its elevated position inside the platform. The region surrounding Baalbek experienced repeated seismic activity throughout recorded history, including destructive earthquakes during the medieval period that devastated portions of the sanctuary. Many upper structures collapsed or suffered extensive damage, yet the enormous retaining stones remained largely intact. Their survival reinforced the impression that the builders achieved something exceptionally durable beneath the visible Roman architecture. The deeper foundations endured while lighter additions above them fractured over time. Few archaeological sites create such persistent disagreement among researchers because the stones challenge both engineering expectations and accepted timelines simultaneously. Some scholars argue that Roman builders themselves completed the entire platform using techniques now poorly understood but still achievable within the organizational power of the empire. Others remain less certain, especially when comparing the megalithic lower platform to later architectural additions constructed above it. Differences in masonry style, construction sequence, and structural appearance have fueled debate for generations regarding whether parts of the deepest foundation may belong to an earlier phase of activity predating the monumental Roman sanctuary. Some historians argue that Roman builders themselves completed the entire platform using techniques now poorly understood, while others believe portions of the lower structure may belong to an earlier phase of construction. This disagreement intensified because Baalbek existed as a sacred site long before the Roman Empire transformed it into Heliopolis, the city of the sun. Archaeological evidence indicates occupation and ritual activity in the area dating back centuries before Roman expansion into the region. If earlier civilizations already considered the location important, questions naturally emerge regarding how much of the massive platform may have existed before Roman architects arrived. Questions surrounding the chronology of the platform intensified once archaeologists began comparing the megalithic foundation to later Roman additions built above it. The contrast between the immense lower stones and certain upper masonry sections appears visually striking even to non-specialists. Some portions of the visible Roman temple complex display construction techniques commonly associated with imperial architecture elsewhere across the Mediterranean, while the deeper megalithic courses possess a more severe and monumental character, difficult to compare directly with ordinary Roman construction patterns. That contrast alone does not prove separate origins, but it continues feeding uncertainty surrounding the true sequence of construction at Baalbek. Long before modern excavation began uncovering deeper sections of the site, travellers and scholars had already noticed that the enormous lower stones appeared strangely different from the architecture resting on top of them. Medieval Arab chroniclers described the ruins with awe, while later European visitors often struggled to believe ordinary human labour could account for the platform's immense scale. Over time, legends involving giants, lost civilizations, or forgotten technologies emerged partly because the visible evidence seemed disconnected from accepted historical expectations. Even today, standing beneath the trilithon creates an unsettling impression difficult to dismiss entirely. The stones do not simply appear ancient, they appear excessive in a way that resists easy explanation. The deeper archaeologists examine the massive platform beneath the Roman temples, the more difficult it became to determine whether the Romans had built the oldest foundations at all. The Romans built the temple, but probably not the foundation. The attribution of the monumental sanctuary at Baalbek to Roman construction has long been accepted as the default explanation, largely because the visible architecture aligns with familiar imperial design. The towering columns, ceremonial courtyards, and formal temple layout fit within the broader architectural language of Roman provincial expansion, where local religious centres were often transformed into imperial cult spaces. On the surface, the site appears to belong comfortably within that tradition, reinforcing the assumption that what stands today is primarily a Roman creation shaped during the height of imperial influence in the eastern Mediterranean. What becomes increasingly difficult to reconcile with that attribution is the behaviour of the platform beneath the Roman temple once it is examined independently of the structures above it. The foundation does not simply support the visible architecture, it behaves as though it belongs to a separate structural system entirely. Instead of acting as a passive base for Roman construction, it introduces its own architectural identity, one defined by scale, mass, and engineering choices that do not always align with the design logic of the upper sanctuary. Roman architectural expansion across the eastern provinces usually followed identifiable construction sequences, yet Baalbek introduces a foundation layer that does not follow those expected patterns. In most Roman sites, foundations are carefully integrated into the planning of the structure above them, designed to distribute weight in predictable ways that reflect standardized engineering principles. At Baalbek, however, the transition between foundation and superstructure feels less like a continuous design and more like a meeting between two different construction philosophies. Before imperial transformation reshaped the site into Heliopolis, the broader region already contained traces of earlier sacred activity that did not begin with Roman occupation. Archaeological evidence from the Bekaa Valley suggests long-term human presence and religious significance extending back into pre-Roman periods, where local traditions shaped the cultural landscape long before imperial integration. This historical continuity complicates the assumption that the Roman sanctuary represents a complete architectural beginning rather than a later phase in a much longer sequence of occupation. When attention shifts to the lowest structural courses, the masonry begins to behave like an independent construction phase rather than a supporting base for later additions. The blocks at this level are not only significantly larger than typical Roman building materials, but are also arranged in a way that suggests a distinct engineering intention. Their presence beneath the visible temple creates the impression of a foundation that may have been designed for something far larger or structurally different from the architecture that ultimately rests upon it. Comparisons with other Roman foundations across the Mediterranean reveal how unusual the Baalbek platform becomes when measured against standard imperial engineering practices. Roman builders were highly consistent in their methods, especially when constructing large civic or religious monuments. Even in their most ambitious projects, they relied on predictable combinations of concrete cores, cut stone facing, and modular construction techniques. The Baalbek foundation, however, stands apart due to the sheer scale of its individual stone blocks and the way they are integrated into the structure as primary load-bearing elements rather than supplementary reinforcement. Across ancient Near Eastern traditions, it was common for new civilizations to build upon older sacred sites, creating layered landscapes where origins often became obscured over time. Temples were rebuilt, expanded, or reinterpreted across generations, with each culture leaving its own architectural imprint while preserving the sacred significance of the location itself. This pattern of reuse does not necessarily imply continuity of construction, but it does suggest continuity of meaning, where the site remains active even as its physical form evolves through successive eras. What remains unresolved in the case of Baalbek is the lack of any direct inscription identifying the builders responsible for the deepest megalithic foundation. Roman monumental architecture typically included dedicatory inscriptions that recorded the patronage of emperors or local elites, often carved directly into visible stone surfaces. While such inscriptions exist in parts of the upper temple complex, they do not extend into the lowest structural layers, leaving the origin of the foundation itself outside the direct historical record. Certain structural elements at the base display construction characteristics that appear inconsistent with typical Roman methods used in comparable large-scale projects. The scale of individual blocks combined with the precision of their placement suggests a construction logic that prioritizes mass stability at an extreme level. While Roman engineers were capable of handling large stone components, the specific configuration seen at Baalbek raises questions about whether the same engineering systems were responsible for both the foundation and the superstructure above it. Interpretations of the site increasingly suggest that multiple construction phases may overlap, rather than a single unified building campaign defining the entire platform. In this view, the visible Roman sanctuary may represent only the latest layer in a much longer architectural sequence, where earlier monumental construction was incorporated into later imperial expansion. Such a model does not require abandoning Roman authorship entirely, but it does complicate the idea that the empire was responsible for initiating the deepest structural level. One possibility raised in archaeological discussions is that Roman builders expanded an already existing monumental base, rather than originating the entire structure themselves. This would place the Roman temple within a broader architectural continuum, where earlier construction phases were preserved, reinforced, and incorporated into a new religious and political framework. The challenge with this interpretation lies not in its plausibility, but in the lack of definitive evidence identifying what came before the Roman transformation. Surviving Roman-era accounts describing the city focus heavily on its religious significance, yet they provide no technical explanation for the origin of the deeper structural layers. Ancient writers were often more concerned with ritual importance and cultural meaning than with engineering detail, meaning that large-scale construction processes frequently remain undocumented. At Baalbek, this absence becomes more significant because the scale of the foundation suggests a level of effort that would normally attract at least some descriptive attention in historical records. As excavation data is analysed in greater detail, the boundary separating Roman additions from earlier masonry becomes increasingly difficult to define with precision. Stratigraphic transitions do not always present clean divisions in ancient construction, particularly in sites that were continuously modified over long periods. At Baalbek, the structural continuity between layers creates ambiguity, making it challenging to assign specific portions of the platform to clearly defined historical phases without introducing interpretive uncertainty. Academic interpretations remain divided, with some researchers supporting a fully Roman origin, while others argue for a pre-Roman foundational structure beneath the visible temple. These positions often depend on how different scholars interpret the relationship between construction style, material scale, and historical continuity. Neither interpretation fully resolves all structural anomalies, which is why the debate remains active rather than settled. Repeated excavation surveys continue to highlight a consistent contrast between the upper Roman architecture and the massive lower platform upon which it rests. The upper structures reflect a well-documented imperial architectural tradition, while the foundation below operates on a scale and material logic that resists simple classification. This contrast does not necessarily indicate different civilizations, but it does suggest a more complex construction history than a single building phase. Throughout the ancient world, sacred sites were often reused across successive civilizations, but Baalbek presents an unusually complex example of this architectural continuity. The scale of the foundation amplifies the difficulty of interpretation, because reuse in most ancient contexts involved adaptation of existing structures rather than the integration of megalithic platforms of such magnitude. Baalbek therefore stretches the concept of reuse into a more ambiguous architectural phenomenon. Even after extensive archaeological investigation, the earliest phase of construction beneath the sanctuary remains without a definitive historical attribution. The absence of conclusive evidence does not eliminate possible explanations, but it prevents any single interpretation from becoming universally accepted within the academic community. As a result, the foundation remains suspended between competing historical narratives. Each additional layer studied beneath the temple further complicates the attempt to separate inherited structures from original construction phases. Instead of revealing a straightforward chronological sequence, the site appears to contain overlapping phases of monumental activity that resist clean segmentation. This layered complexity suggests that Baalbek cannot be fully understood through a single construction narrative alone. The deeper the investigation descends below the Roman level, the more uncertain the assumption becomes that the empire was responsible for the entire platform. What begins as a clearly identifiable Roman sanctuary gradually transforms into a structure whose earliest origins remain unresolved within current historical frameworks. Regardless of when the foundation was first established beneath Baalbek, the physical problem of moving stones of that magnitude still defies any complete explanation. Moving 1,000-ton stone should have been impossible. When mass reaches the scale of the Baalbek monoliths, ordinary assumptions about stone behavior begin to break down under their own weight. At that point, the problem is no longer purely archaeological or historical, but physical in the most immediate sense, where the properties of limestone, friction, and inertia begin to define what is even theoretically possible. The question surrounding Baalbek shifts from how the stones were shaped and placed into existence to something more fundamental: how they could ever be set in motion at all without fracturing, collapsing, or becoming immovable under their own resistance. Even before transport begins, the stone effectively becomes a system of internal forces that must be controlled as much as it is moved. Across the transport corridors surrounding Baalbek, the landscape introduces a persistent resistance problem that no simple dragging method could easily overcome. The terrain between the quarry zones and the temple platform is not a flat engineered surface, but a combination of uneven gradients, compacted earth, and natural rock formations that would have created unpredictable friction points. Even minor irregularities in the ground surface would have significantly altered the stability of a moving object weighing hundreds of tons, turning controlled movement into a constant struggle against shifting balance and localized stress. At scale, the ground ceases to behave as passive support and becomes an active participant in the mechanics of transport. At the human scale, even coordinated labor systems documented in the ancient world begin to lose effectiveness when confronted with loads approaching 1,000 tons. Ancient engineering projects were capable of remarkable achievements when distributing weight across large groups of workers, but coordination efficiency decreases rapidly as both distance and resistance increase. The physical effort required to initiate movement in a single direction becomes exponentially more difficult as inertia increases, meaning that simply adding more labour does not solve the underlying mechanical limitation imposed by mass itself. Beyond a certain threshold, additional manpower introduces diminishing returns rather than proportional gain. One widely discussed reconstruction model proposes that the stones were moved using extended earthen ramps, gradually built up to the level of the construction site. In this scenario, massive quantities of earth, stone, and debris would have been required to construct a stable incline capable of supporting continuous transport. The idea relies on reducing vertical lifting demands by converting them into a gradual horizontal ascent, allowing the stones to be dragged or slid upward over an extended surface rather than lifted directly. However, the structural integrity of such ramps becomes increasingly difficult to maintain, as both length and load increase simultaneously. The difficulty with ramp-based theories emerges when calculating the sheer volume of material required to sustain a stable incline capable of supporting such extreme weight. As the slope increases in length to maintain a manageable gradient, the amount of construction material needed expands dramatically, eventually rivaling or exceeding the scale of the construction itself. This introduces a logistical contradiction, where the infrastructure required to move the stones becomes almost as monumental as the temple platform they were intended to support. At that point, the transport system begins to resemble a second construction project rather than a method of construction. Alternative interpretations suggest the use of rolling elements placed beneath the stone, converting static friction into a controlled sequence of incremental movement. In this model, logs or cylindrical supports would be positioned beneath the block, allowing it to be rolled forward gradually as each segment was repositioned. While this method is documented in various ancient contexts, its effectiveness decreases significantly when applied to extremely heavy loads, where pressure quickly deforms or crushes the supporting elements. Under extreme mass, the rolling medium itself becomes a consumable resource rather than a stable mechanism. Mechanical advantage systems based on pulleys and lifting frames appear in Roman engineering records, yet their documented capacity falls far below what Baalbek would require. Roman architects demonstrated a sophisticated understanding of load distribution and mechanical lifting, particularly in the construction of large temples, amphitheatres, and public works. However, even their most advanced lifting devices were typically designed for modular components, not single monolithic stones approaching the upper limits of known ancient weight handling. Scaling these systems upward introduces exponential increases in structural stress that exceed their original design logic. Even when multiple methods are combined in theoretical models, the transition from horizontal movement to elevated placement remains the most unstable phase of the entire process. This is the point at which controlled motion must become controlled elevation, requiring precise synchronization of force, balance, and structural support. Any loss of coordination during this phase would not simply slow progress, but risk catastrophic failure of both the transport system and the stone itself. The system must shift from movement control to positional precision, a transition that dramatically increases operational risk. Terrain analysis around the temple complex shows uneven gradients that would have complicated any attempt at maintaining consistent directional force. The ground is not uniformly supportive, meaning that pressure beneath a moving stone would fluctuate continuously as it passed over different surfaces. These variations would have required constant adjustment from labourers and engineers attempting to stabilise the load, making uninterrupted movement extremely difficult to maintain over long distances. Each shift in terrain introduces a new mechanical problem that must be resolved in real time. At this scale, even slight variations in soil density can produce uneven load distribution that shifts dynamically during movement rather than remaining fixed. This means that the stone would not experience a consistent resistance profile, but a constantly changing pattern of support and drag. In practical terms, this creates a situation where forward motion must be continuously corrected in real time, since any delay in adjustment allows imbalance to accumulate. The larger the mass, the less tolerant the system becomes to these micro-variations, turning what would be negligible at smaller scales into a critical instability factor during transport. Some engineering reconstructions attempt to distribute the load across thousands of workers, yet coordination efficiency decreases sharply as distance and weight increase simultaneously. Large-scale labour systems rely on synchronization, but as more individuals are added to a movement system, small delays in timing and force application accumulate into larger instability. At the scale required for Baalbek, even minor inconsistencies in timing could introduce dangerous oscillations in the movement of the stone. The system becomes increasingly sensitive to human-level variability. The physics of limestone at extreme mass introduces additional uncertainty as internal stress distribution becomes increasingly unpredictable under dynamic movement. A stationary block of stone behaves differently from one in motion, particularly when subjected to uneven forces during transport. Internal fractures, even if invisible at the surface, can expand under shifting pressure, meaning that the process of moving the stone carries inherent structural risks that increase with every attempt at acceleration or direction change. Motion itself becomes a form of stress test on the material, each proposed transport system encounters a critical failure point when the combined effects of friction, inertia, and structural control are calculated together. Individually, each method offers a partial explanation for how movement might have been initiated or sustained, but when combined into a full sequence of transport, the systems begin to interfere with one another. Frictional resistance increases under load, inertia resists directional change, and structural control becomes harder to maintain as external forces fluctuate. The interaction between these forces produces instability that is not easily isolated or corrected. Ancient construction methods in other civilizations demonstrate impressive heavy lift capabilities, but none operate convincingly at the scale required for the Baalbek stones. Monumental architecture in Egypt, Greece, and Rome often relied on combinations of ramps, sledges, and coordinated manpower, yet those systems were generally designed for smaller modular components rather than singular blocks of extreme mass. Baalbek extends beyond these known limits, placing it in a category where comparison itself becomes uncertain. The scale shifts the problem outside typical historical engineering reference points. The problem intensifies when considering the final approach to the platform, where elevation and alignment would have demanded precise control over a moving object of extraordinary inertia. Even if the stones were successfully transported across level ground, positioning them at the required height introduces a second layer of difficulty involving vertical control and fine adjustment. At this stage, the system would have needed to shift from brute force movement to controlled placement, a transition that significantly increases the risk of failure. Precision replaces power as the limiting constraint. Some researchers propose staged movement sequences, where stones were gradually repositioned over extended periods rather than moved in a single continuous action. This would involve incremental advances, with pauses for stabilization and repositioning of supporting structures along the route. While such a method reduces immediate stress on the system, it also extends the duration of exposure to environmental and structural risks, increasing the complexity of long-term coordination. Time itself becomes an additional engineering variable. Even within these gradual models, the energy required to overcome initial static resistance remains one of the most difficult variables to resolve. Static friction at extreme weight levels requires a force threshold significantly higher than that needed to maintain motion once movement has begun. This means that initiating movement would have been the most critical and potentially most failure-prone stage of the entire process. Once overcome, the system enters a less resistant but still unstable dynamic state. Comparative studies of ancient engineering suggest that known transport technologies consistently converge on similar upper limits long before reaching Baalbek's scale. Across multiple civilizations, the practical ceiling for monolithic transport appears to fall well below the estimated mass of the largest stones used in the platform. This suggests that Baalbek either represents an extreme outlier in ancient engineering capability, or a case where multiple undocumented or poorly understood techniques may have been combined in ways not yet fully reconstructed. The absence of parallel examples increases the interpretive difficulty. The most persistent challenge across all reconstructions is not the availability of labour or tools, but the inability to maintain controlled movement once motion begins. Once a stone of this scale begins to shift, every variable — friction, balance, terrain resistance, and structural integrity — must remain simultaneously stable, a condition that becomes increasingly difficult to sustain as distance increases. As each theoretical model is examined in detail, a repeating pattern emerges where the explanation functions locally, but collapses under full-scale application. The system works in fragments, but not as a whole, because regardless of which method is considered, every attempt to reconstruct the movement of the Baalbek monoliths ultimately breaks down at the same physical threshold. Every modern reconstruction begins to fail at the same point. Contemporary heavy lifting technology is capable of generating forces that would have been unimaginable in earlier engineering eras, yet those capabilities begin to lose clarity when applied to extreme-scale transport problems. Modern cranes, hydraulic platforms, and modular lifting systems operate with precision that allows industries to move components measured in hundreds of tons with controlled stability. But that control depends heavily on predictable load behavior, stable ground conditions, and well-distributed structural feedback. When those assumptions are removed, and the scale is pushed toward the estimated mass of the Baalbek monoliths, The system no longer behaves as a straightforward extension of known engineering principles. Instead, each increase in capacity introduces new forms of instability that are not proportional but exponential in their complexity. What appears manageable in controlled industrial contexts begins to fragment into interdependent failure risks once every variable is scaled simultaneously. When modern crane systems are theoretically scaled to match the estimated weight of the Baalbek monoliths, structural efficiency no longer increases linearly or predictably. In industrial engineering, lifting capacity is not simply a matter of multiplying strength, because every additional unit of load introduces new stress pathways through cables, joints, and support structures. At extreme levels, these stresses begin to interact in unpredictable ways, meaning that a system designed for balance under one set of conditions may become unstable when scaled beyond its tested limits. The result is not a stronger version of the same system, but a fundamentally different mechanical environment where standard assumptions about safety margins and force distribution begin to lose reliability. At this scale, even reinforcement strategies begin to produce diminishing returns. At the highest levels of load simulation, the relationship between force distribution and structural stability begins to break down under conditions of sustained pressure. In controlled engineering environments, forces can be mapped and predicted with high accuracy when systems remain within defined thresholds. However, as mass increases beyond those thresholds, localized stress points begin to form in ways that are difficult to anticipate. These stress concentrations do not remain static. They shift dynamically as load is applied, creating feedback loops within the structure that gradually reduce overall stability, even when external conditions appear unchanged. Over time, these internal redistributions become the primary source of system failure rather than external overload. Computer-based reconstruction models designed to simulate multi-ton stone movement repeatedly converge on a narrow set of failure conditions regardless of the variables applied. Whether the simulations involve rolling systems, ramp-based transport, or multi-point lifting frameworks, the outcomes tend to stabilize around similar breakdown points. This consistency suggests that the limitation is not tied to a single method, but to a deeper constraint imposed by the interaction between mass, friction, and structural coordination. Even when idealized conditions are assumed, the models still encounter a point where controlled motion becomes mathematically possible only in theory, not in sustained physical application. The gap between theoretical motion and sustained motion becomes the central obstacle. Even controlled experimental setups using reinforced materials demonstrate that incremental movement becomes unstable once load thresholds approach the upper limits of industrial lifting design. Scaled experiments using heavy blocks and reinforced transport platforms show that initial movement can often be achieved through carefully distributed force. However, maintaining that movement over distance introduces accumulating instability, particularly when alignment shifts even slightly. The challenge is not initiating motion, but preserving equilibrium throughout the process, as small deviations in force application gradually amplify into structural imbalance that becomes increasingly difficult to correct. At larger scales, this correction window narrows dramatically. Hydraulic lifting systems, while highly advanced in controlled environments, encounter increasing unpredictability when lateral resistance and uneven terrain are introduced simultaneously. These systems are designed to operate under conditions where surfaces are stable and loads are evenly distributed across multiple support points. When those conditions are disrupted by irregular ground composition or shifting resistance beneath the load, the hydraulic response becomes less predictable. Pressure must constantly adjust in real time, and even minor delays in that adjustment can result in uneven lifting, which at extreme scales introduces significant risk of system failure. The system begins to react to instability faster than it can resolve it. Engineering attempts to replicate large-scale dragging or sliding systems reveal that frictional variance becomes a dominant destabilizing factor at extreme mass levels. Friction is often treated as a predictable resistance force in smaller systems, but at large scales it becomes highly irregular due to variations in surface composition, pressure distribution, and environmental conditions. A stone of extreme weight does not interact uniformly with the ground beneath it. Instead, it creates shifting zones of resistance that change continuously as movement begins. This variability makes sustained, controlled transport significantly more difficult than initial calculations often suggest. The ground itself becomes part of the instability. In full-scale theoretical models, the transition from static support to dynamic motion consistently produces stress concentrations that exceed safe structural limits. The moment a stationary object begins to move under extreme load, the system must overcome static friction, which is significantly higher than kinetic friction. This transition creates a sudden redistribution of forces throughout the structure, and at extreme mass levels, this redistribution can exceed the tolerances of both the load-bearing material and the transport system itself. The result is a brief but critical phase where stability is most likely to fail. This transition phase becomes the most vulnerable moment in the entire process. Terrain interaction simulations show that even minor irregularities in ground composition can dramatically alter load behavior during movement attempts. Variations in soil density, hidden voids, or uneven rock formations beneath the surface introduce unpredictable shifts in resistance. At small scales, these variations are manageable, but when the load reaches extreme weight levels, even minor inconsistencies can redirect force in ways that destabilize the entire system. The ground ceases to function as a neutral surface and instead becomes an active variable in the transport process. Stability becomes dependent on environmental precision rather than mechanical control. Distributed force strategies involving multiple synchronized lifting points appear effective in isolation but lose reliability when applied across extended distances. These systems rely on precise coordination between multiple mechanical units or groups of labor acting in unison. As distance increases, synchronization becomes more difficult to maintain, and even slight timing discrepancies between lifting points can create uneven force distribution. At extreme scale, these discrepancies accumulate quickly, undermining the stability of the entire operation. Coordination becomes more fragile than force itself. Material stress analysis of large limestone blocks indicates that internal fracture propagation becomes more likely under uneven acceleration patterns. Limestone, while relatively strong under compression, responds differently when subjected to dynamic forces that are not evenly distributed. Sudden changes in acceleration or directional force can cause internal stress lines to expand, even when external surfaces appear intact. This means that movement itself introduces structural risk, particularly when the load is not perfectly balanced throughout the transport process. The act of moving becomes structurally transformative rather than purely mechanical. Every modern reconstruction that incorporates real-world engineering constraints encounters a recurring point where system coordination collapses under cumulative load interaction. Whether the model relies on mechanical lifting, sliding, rolling, or hybrid approaches, the same fundamental issue emerges. The system can function in controlled segments, but fails when all variables must operate simultaneously under full-scale conditions. The interaction between force, friction, alignment, and structural stability creates a network of dependencies that becomes increasingly difficult to manage as scale increases. The failure is not sudden, but cumulative. Comparative testing across different transport models reveals that increasing mechanical complexity does not resolve the underlying instability problem. Adding additional lifting points, support structures, or stabilization mechanisms may improve local control, but it also introduces more variables that must be synchronized. At extreme scale, this added complexity increases the number of potential failure points rather than eliminating them, meaning that the system becomes more fragile despite appearing more capable on paper. Complexity shifts from solution to liability. Attempts to combine multiple lifting and sliding methods into hybrid systems introduce additional synchronization challenges that further reduce overall efficiency. These hybrid approaches often aim to distribute load more effectively by blending different engineering principles, but each method operates under different physical assumptions. When combined, these assumptions can conflict, leading to interference between mechanical systems that were not originally designed to function together under extreme conditions. The result is not integration, but competition between forces. Even under idealized conditions, simulations consistently demonstrate that maintaining directional control over extreme mass objects becomes progressively more difficult as motion continues. Initial movement may appear stable, but as distance increases, small deviations in force application begin to accumulate. These deviations gradually alter the trajectory of the load, requiring constant correction that becomes increasingly difficult to sustain without introducing further instability. Control shifts from active guidance to constant correction. field experiments conducted with scaled analogues confirm that small deviations in alignment rapidly amplify into structural instability at larger scales. What begins as a minor imbalance at the start of movement can evolve into significant displacement by the time the load reaches even a moderate distance. This scaling effect suggests that precision tolerances become tighter, not looser, as size increases, placing additional demands on coordination that exceed typical operational limits. Precision becomes more restrictive as scale expands. Across engineering literature, known upper limits of material transport systems converge well below the estimated requirements posed by Baalbek scale monoliths. While modern industry has achieved remarkable progress in heavy transport, those achievements remain bound by physical constraints that are well documented and consistently observed across multiple disciplines. The gap between those known limits and the requirements implied by the Baalbek stones remains significant, even when theoretical optimizations are applied. This gap persists regardless of technological advancement. As each reconstruction model is pushed toward real-world constraints, the same operational breakdown point appears regardless of design approach. This convergence suggests that the limitation is not method-specific but structural, emerging from the interaction of multiple physical factors that cannot be fully separated at an extreme scale. The result is a consistent pattern of partial success, followed by unavoidable failure at a predictable threshold. The failure point itself becomes the most consistent finding. What makes this convergence more significant is that the failure point does not shift, even when variables are deliberately simplified or idealized. Reducing the system to only its most favorable conditions does not eliminate the breakdown, but instead delays it slightly before the same structural limits reappear. This suggests that the constraint is not external, but embedded within the interaction of scale and coordination itself. At extreme mass levels, even small inefficiencies in timing or force alignment become amplified through the system, creating instability that cannot be compensated for by additional capacity alone. The most persistent limitation across all modern attempts is not force generation itself, but the inability to maintain coordinated stability throughout the entire movement process. Machines and systems can generate enormous power, but sustaining that power in a controlled, continuous and precisely aligned direction under extreme load proves to be the central challenge. Stability, rather than strength, becomes the limiting factor. The system fails not from lack of capability, but from loss of coordination. Every modern reconstruction collapses at the same unresolved threshold, so attention inevitably returns to the physical evidence preserved within the stone itself. Strange details in the stonework suggest a lost construction method. Surface examination of the limestone reveals an unusual level of refinement in certain sections that does not align with typical expectations of large-scale ancient masonry work. At Baalbek, where the lower platform is composed of enormous stone blocks, attention often shifts towards scale first, yet it is the close inspection of surfaces that introduces a different kind of uncertainty. Instead of rough, purely functional shaping, some areas show deliberate smoothing and precision finishing that suggests a level of control extending beyond basic structural necessity. Within the joint interfaces of the platform at Baalbek, the alignment between adjacent blocks demonstrates a consistency that becomes increasingly difficult to dismiss as incidental. The contact points between stones are not uniformly rough or uneven, but in certain zones they appear to meet with a degree of continuity that requires careful geometric planning. These joints do not simply hold massive stones together, they distribute contact in a way that implies intentional shaping of both surface bifurcaire to final placement. Cut marks preserved along several exposed stone faces indicate a repetition pattern that suggests controlled removal rather than irregular shaping. Instead of random tool impressions scattered across the surface, there are sections where marks appear parallel, deliberate and consistently spaced. This type of patterning raises questions about the tools and techniques used, since repeated uniformity at this scale is difficult to achieve without a stable method of controlled cutting and finishing. When these finishing techniques are compared with other known ancient construction sites, the degree of uniformity at Baalbek stands out as significantly more precise in specific structural zones. Across many ancient monuments, tool marks typically vary due to differences in material resistance, worker technique, and environmental conditions during construction. At Baalbek, however, certain sections display a level of consistency that reduces this expected variability, suggesting a more controlled or specialized approach to surface preparation. What complicates standard interpretation is the relationship between rough foundational surfaces and highly refined visible edges within the same structural layers. In many places, the lower contact surfaces of the stones appear minimally worked, while adjacent visible faces show a higher degree of finishing. This contrast within a single block suggests that different stages of processing were applied selectively rather than uniformly, potentially reflecting distinct functional requirements during construction. Certain stone interfaces show interlocking behavior that requires a level of geometric planning not typically associated with large monolithic assembly methods. The way some blocks meet does not rely solely on weight and gravity for stability, but appears to involve subtle shaping that guides how surfaces settle against one another. This introduces the possibility that alignment was achieved through more than just placement, but through pre-designed contact geometry embedded into the stone itself. Notably missing from many exposed surfaces is the expected variation in tool impressions that usually appears in manually worked limestone of comparable scale. In most large stone constructions, differences in pressure, angle and tool wear leave a broad range of surface signatures. At Baalbek, certain areas reduce this variability, presenting instead a more uniform texture that does not easily match standard expectations of manual finishing processes. Quarry-related markings preserved on select blocks suggest stages of extraction and finishing that are not fully represented in surviving construction sequences. Some surfaces retain traces that appear to originate from initial removal phases, while others indicate later refinement, yet the transition between these stages is not always clearly defined. This incomplete sequence of visible processing leaves gaps in understanding how raw material became integrated into such precise structural alignment. In several sections of the platform, the transition between rough-cut stone and polished contact surfaces occurs with abrupt precision rather than gradual refinement. Instead of a smooth progression from coarse to finished texture, the change can occur within a short boundary area on the same block. This suggests that finishing techniques may have been applied selectively to specific functional zones, rather than distributed evenly across the entire surface. Microscopic irregularities along some edges imply controlled finishing processes that may have been applied under conditions of sustained structural constraint. These small deviations are not random imperfections, but appear in patterns that suggest intentional adjustment during or after shaping. Such fine control at large-scale construction raises questions about how stability and precision were maintained simultaneously during assembly. Structural comparison between different sections of the foundation reveals inconsistencies in finishing style that may indicate multiple construction approaches operating in parallel. Some areas emphasize tight jointing and refined surfaces, while others prioritize mass and raw stability with minimal finishing. This variation does not necessarily imply different periods of construction, but it does suggest differing priorities or techniques applied within the same structural system. Across the platform, the precision of certain joints appears to exceed what would normally be required for purely functional load distribution at this scale. In many large stone constructions, joints are designed to be strong rather than visually or geometrically refined. At Baalbek, however, some joints exhibit a level of alignment accuracy that goes beyond structural necessity, introducing the possibility that precision itself was an intended outcome of the construction process. Some preserved stone faces exhibit a level of surface regularity that challenges straightforward categorization within known ancient tooling limitations. The smoothness and consistency in certain areas suggest a finishing process that is difficult to fully reconcile with conventional hand tool methods alone. While this does not imply unknown technology, it does highlight a gap between observed results and the range of expected techniques. The distribution of contact points between massive blocks suggests an intentional optimization of a load transfer that is not uniformly applied throughout the structure. In some areas, pressure appears to be carefully directed through specific contact zones, while in others it is more broadly distributed. This uneven application of structural logic indicates that different engineering priorities may have influenced different sections of the platform during construction. Variations in surface treatment across adjacent blocks imply that different stages of processing may have occurred under distinct methodological conditions. Some blocks appear to have been finished with greater refinement before placement, while others show signs of post-placement adjustment. This suggests a construction process that was not entirely linear, but potentially adaptive, responding to structural needs as assembly progressed. When viewed collectively, these small but consistent irregularities begin to form a pattern that does not easily conform to standard archaeological classification. Individually, each detail can be explained within known construction practices, but together they produce a layered complexity that resists simple categorization. The result is a stone structure that appears both familiar in material and unfamiliar in execution. The absence of clearly identifiable construction signatures in certain zones raises further questions about how the final assembly phase was actually executed. Without consistent tool marks or standardized finishing traces across all areas, it becomes difficult to reconstruct a single unified method of construction. Instead, the evidence suggests a process that may have varied in technique depending on location, function, or stage of completion. As more sections of the stonework are analysed in detail, the gap between expected tooling evidence and observed surface characteristics becomes increasingly pronounced. The deeper the inspection goes, the more the structure reveals inconsistencies that do not align neatly with any single known construction tradition. These inconsistencies do not necessarily imply mystery in the sensational sense, but they do indicate unresolved technical questions about method and process. Each layer of preserved masonry introduces additional uncertainty regarding the exact sequence of shaping, fitting, and placement operations involved in construction. The further the analysis progresses, the less certain the chronological order of these processes becomes, especially when multiple surface treatments appear within the same structural context. This creates a layered architectural record that is difficult to reconstruct with full confidence. These persistent irregularities in the stonework ultimately suggest not only unusual methods of construction, but a structural integrity that continues to define how the platform behaves long after its original assembly. The platform survived earthquakes that destroyed entire cities. Historical records of seismic activity across the Levant consistently describe cycles of destruction that reshaped entire cities over successive centuries of geological instability. In the Eastern Mediterranean, earthquake events are not isolated anomalies, but recurring forces that have repeatedly altered settlement patterns, architectural continuity, and urban survival. Within this long environmental record, stone-built cities often carry visible evidence of collapse and reconstruction, where layers of damage accumulate as physical testimony to repeated ground movement over time. Archaeological surveys of nearby ancient settlements reveal repeated structural collapse patterns that align closely with known regional earthquake events affecting the Eastern Mediterranean basin. Cities situated within the same seismic corridors as Baalbek often show similar damage signatures, including fractured walls, displaced foundations, and partially preserved monuments that indicate sudden structural failure. These patterns are not random, but correspond to documented seismic episodes that have historically impacted the Levant, shaping how ancient communities rebuilt or abandoned their architectural centres. What distinguishes the lower platform at Baalbek from surrounding ruins is not its size, but the way it remains partially intact while adjacent monumental structures have failed. In many nearby archaeological sites, temple complexes and civic buildings show extensive fragmentation, with only foundations or scattered blocks remaining in place. At Baalbek, however, the deepest structural layers continue to define a coherent base, even when upper sections have suffered visible collapse or long-term degradation. Across successive historical periods, seismic events have repeatedly altered the architectural landscape of the region, leaving behind layers of destruction that reflect both magnitude and frequency of ground movement. These events have not only damaged individual structures, but have also reshaped entire urban layouts, forcing repeated cycles of repair, abandonment, and rebuilding. In this context, survival becomes a significant and archaeological marker as destruction, since it highlights which structural systems were able to withstand repeated environmental stress. In contrast to nearby ancient complexes that show extensive structural fragmentation, the Baalbek platform demonstrates a level of foundational stability that appears inconsistent with typical masonry behaviour under lateral stress. Most stone structures subjected to repeated seismic forces exhibit progressive weakening along joints, corners, and load-bearing transitions. Yet at Baalbek, the lowest courses of stonework continue to present a stable geometric arrangement that does not fully correspond to the expected failure patterns seen in comparable ancient constructions. When subjected to earthquake-driven ground displacement, most ancient foundations exhibit predictable failure points where load distribution becomes uneven and structural integrity begins to collapse. These failure points often emerge at structural interfaces where different materials or construction phases meet. As seismic waves travel through the ground, they create alternating zones of compression and tension that exploit any structural weakness, leading to visible cracking or displacement over time. Comparative analysis of regional temple sites shows that structures built with similar materials and techniques often respond differently to identical seismic conditions, depending on foundation depth and mass distribution. Lighter structures tend to shift or fragment more easily, while heavier, more integrated foundations distribute energy differently across their base. This variation in response is well documented in archaeological and geological studies, which highlight how structural mass can influence survivability during repeated seismic exposure. The survival of the Baalbek lower platform becomes more striking when viewed alongside documented cases of total structural failure in neighbouring cities exposed to the same seismic zones. Across the region, entire urban centres have been reduced to ruins by major earthquakes, leaving behind fragmented architectural remains and displaced stonework. Against this backdrop of widespread destruction, the persistence of a coherent megalithic base introduces a structural outcome that stands apart from expected regional patterns. Geological assessments of the Bakar Valley indicate repeated fault activity that has historically generated significant ground movement capable of dismantling large-scale architectural systems. The valley sits within a complex tectonic region where stress accumulation along fault lines has produced periodic seismic events over millennia. These movements have shaped not only the natural landscape but also the long-term stability of human-built environments across the region. Within this context of persistent seismic instability, the persistence of massive stonework at Baalbek introduces a structural outcome that does not fully align with expected engineering responses. While most ancient foundations exhibit cumulative damage over time, the deepest sections of the platform appear to maintain a level of integrity that resists the progressive degradation typically associated with repeated ground motion. This divergence raises questions about how force distribution is managed within such a large and dense stone structure. Layers of collapsed debris found in surrounding archaeological sites provide clear evidence of repeated rebuilding cycles following major earthquake events across the region. These layers often contain remnants of previous architectural phases, buried beneath later construction, as communities rebuilt on top of damaged or destroyed structures. At Baalbek, however, the deepest surviving layers appear less disrupted by this cycle, suggesting a different structural response to long-term seismic pressure. The lower platform's ability to remain largely stable, while upper architectural elements suffered damage, suggests a differential response to seismic force distribution. In many multi-layered stone structures, upper sections are more vulnerable to lateral movement, while lower foundations absorb and distribute stress more evenly. At Baalbek, this distinction becomes more pronounced, as the upper Roman-era structures show significantly more visible damage compared to the massive base beneath them. In many ancient construction systems, structural failure tends to initiate at connection points between load-bearing elements, yet this pattern is less pronounced in the deepest sections of Baalbek's foundation. These lower courses of stone are tightly integrated, with minimal visible separation between blocks in key areas, reducing the number of weak points where seismic stress might accumulate. This continuity of structure may contribute to the platform's long-term stability under repeated environmental stress. Seismic modelling of large stone assemblies demonstrates that mass concentration at the foundation level can significantly alter how energy from ground movement is absorbed and dissipated. Heavier foundations tend to shift seismic energy deeper into the ground, reducing the amplitude of movement transmitted to upper structures. This principle is widely recognised in modern engineering, yet its application at the scale and precision observed at Baalbek remains difficult to fully replicate in reconstructed models. Even when exposed to repeated cycles of seismic stress, the base layers of the platform show fewer signs of progressive structural weakening than expected under long-term environmental strain. Over time, most stone structures develop visible indicators of fatigue, including widening joints, displaced blocks, and microfracturing. At Baalbek, these indicators are present in surrounding structures, but appear less concentrated within the deepest surviving foundation layers. Across the historical timeline of the region, successive earthquakes have erased entire urban centres, leaving only fragmentary traces of once stable architectural systems. Cities have been reduced to foundations and scattered stonework, often requiring extensive reconstruction or complete abandonment. In this broader pattern of destruction, the survival of a coherent monumental base becomes increasingly unusual when compared with regional archaeological records. The endurance of the Baalbek platform becomes increasingly difficult to attribute solely to conventional construction resilience when compared with the widespread destruction observed elsewhere. While material strength and structural mass certainly contribute to stability, they do not fully account for the consistency with which the lowest layers of the platform remain intact across repeated seismic events. This discrepancy introduces a deeper question about how foundational systems were originally configured. As structural remains across the Levant are examined collectively, a recurring pattern emerges where most foundations fail under similar seismic thresholds, with few notable exceptions. This consistency suggests that regional construction systems generally respond predictably to environmental stress, making outliers particularly significant when they do not follow expected failure behaviour. The most persistent question arising from this comparison is not why surrounding structures collapsed, but why this particular platform maintained its integrity under comparable conditions. The contrast between widespread destruction and localized endurance shifts attention away from surface-level explanations and toward deeper structural properties embedded within the foundation itself. That pattern of resistance leads the investigation below the visible structure, where deeper excavation begins to suggest the presence of an earlier architectural phase beneath the surviving platform. Excavations beneath the temple revealed something older. Archaeological work at Baalbek originally focused on documenting the visible platform rather than investigating any deeper structural phases that might exist beyond it. The priority was to map, record and preserve what could already be seen above ground, especially the massive stone foundation that dominates the site. At this stage, there was no expectation that the monument's most significant information might lie outside the visible architecture, and the work was framed within a conventional understanding of Roman-era construction sequences. Removal of upper debris layers uncovered compact sediment sequences that did not immediately correspond with the established construction timeline of the monument above. These layers appeared compressed and accumulated over long periods, containing mixed material that reflected both natural deposition and human activity. Rather than revealing a straightforward continuation of architectural development, the early stages of clearance introduced ambiguity about how many historical phases were actually preserved within the same vertical space. Continued clearing past the recognized foundation boundary revealed structural discontinuities that interrupted the expected progression of architectural development. Instead of a clear transition from built structure to natural ground, the excavation encountered irregular breaks where material composition and alignment no longer followed a predictable pattern. These interruptions suggested that the site's formation history might not be linear, but instead composed of overlapping construction episodes. A distinct set of stone formations emerged at a level where no clearly documented construction phase had previously been recorded. These formations were not isolated fragments, but arranged in ways that implied intentional placement. Their presence beneath the known foundation introduced the possibility that the visible platform rests upon an earlier structural system that has not been fully accounted for in established interpretations. Structural ordering within these newly exposed elements did not match the geometric logic observed in the upper platform construction. While the visible monument follows a consistent and massive block-based arrangement, the underlying features exhibited variations in alignment and spacing that did not conform to the same structural principles. This divergence raised questions about whether different architectural systems were operating at different stages of the site's development. Changes in material consistency across successive layers suggested that the site may have undergone more than one distinct building methodology. Some layers appeared tightly compacted and deliberately shaped, while others retained more irregular compositions that hinted at different construction conditions or techniques. The contrast between these materials implied that the site's formation process may not belong to a single unified architectural phase. Evidence from stratified profiles indicated that certain built components were positioned atop earlier formations rather than natural bedrock. This arrangement complicates the assumption that the visible foundation directly rests on an untouched geological base. Instead, it suggests that earlier structural elements may have already existed at the location before the current platform was established, creating a layered architectural foundation. Irregular contact zones between construction phases showed no smooth transition, typically expected in gradual architectural development. In many well-documented ancient structures, transitions between phases are marked by relatively consistent interfaces. At Baalbek, however, some of these interfaces appear uneven and fragmented, making it difficult to determine whether they represent intentional construction layering or later modification. Field documentation recorded instances where lower structural fragments displayed finishing characteristics inconsistent with their buried position. In certain cases, surfaces that would normally remain concealed showed levels of refinement that are unexpected for elements positioned beneath a monumental foundation. This discrepancy introduces further uncertainty about the sequence in which different parts of the structure were completed. Partially defined architectural traces beneath the main platform introduced uncertainty regarding how many construction phases the site actually contains. These traces do not form complete structures in isolation, yet they suggest that additional architectural activity may have occurred before or beneath the visible monument. The incomplete nature of these features leaves their function and origin open to interpretation. Directional alignment within some buried structures diverge from the orientation pattern established in the visible temple complex. While the upper construction follows a coherent spatial orientation, certain lower elements appear rotated or offset relative to that system. This misalignment suggests that different planning frameworks may have been used at different stages of the site's development. The vertical arrangement of materials exposed during investigation revealed a complexity extending beyond conventional single-phase construction models. Instead of a simple foundation-to-structure progression, the site presents multiple stacked layers with varying structural logic. This complexity challenges straightforward explanations based on a single construction episode. Shifts in construction technique between adjacent layers implied that different building systems may have been applied at different stages. Some sections show evidence of large-scale block placement, while others indicate more irregular or adaptive construction methods. The coexistence of these approaches within the same vertical profile suggests a more complex architectural history than previously assumed. Certain subsurface segments appeared physically integrated with overlying structures in ways that suggested deliberate continuity rather than later intrusion. These connections are not random overlaps, but appear structurally aligned in specific zones. This raises the possibility that lower and upper elements were designed with some awareness of one another, even if separated by time. Among the uncovered formations were stone configurations that could not be confidently matched with any known architectural system from the surface level. These configurations do not directly correspond to the visible monument above, nor do they clearly align with other documented regional construction styles. Their function remains uncertain within the current framework of interpretation. As additional material was removed, the boundary separating engineered construction from natural geological formation became increasingly ambiguous in specific zones. In some areas, it is difficult to determine where deliberate shaping ends and natural rock formation begins. This ambiguity complicates efforts to define the exact extent of human modification at the site. Attempts to align buried features with known regional construction traditions produced inconsistencies that resisted clear classification. While certain elements share broad similarities with ancient building practices in the region, others do not fit comfortably within any established category. This inconsistency prevents a definitive assignment of cultural or chronological origin. Each newly exposed section introduced additional structural variables rather than reducing uncertainty about the site's development sequence. Instead of clarifying the architectural history, a deeper investigation expanded the number of unresolved questions. The accumulation of these variables suggests that the site's formation may involve more complex processes than initially anticipated. The accumulating architectural evidence suggested a construction history that may extend beyond the chronological framework normally associated with the monument. Rather than fitting neatly within a single historical period, the site appears to contain overlapping layers that may reflect a longer and more complex sequence of development than traditionally assumed. The layered structures below the platform suggest a reality that later historical accounts struggle to describe with clarity or agreement. ancient writers could not explain what they were seeing. Early written accounts describing the site consistently frame the monumental platform at Baalbek in terms that reveal both awe and uncertainty about its origin and construction. These descriptions rarely present the structure as something fully understood by those who recorded it, instead emphasizing its extraordinary scale and the difficulty of placing it within familiar architectural categories. What survives in these texts is not a technical explanation, but a repeated sense of encountering something that resisted ordinary interpretation. Travellers passing through the region recorded impressions of the structure that often emphasized its overwhelming scale rather than any clear understanding of how it had been built. Many accounts focus on the sheer presence of the platform, describing its imposing mass in ways that suggest it dominated the surrounding landscape. The emphasis tends to fall on perception rather than explanation, as though the structure itself overwhelmed the observer's ability to analyze it in structural terms. In several surviving accounts, the monument is described in ways that suggest observers struggled to reconcile what they were seeing with familiar architectural expectations of their time. Rather than fitting neatly into known categories of temples or civic buildings, the structure appears to have been treated as an exception, something that did not behave like other known constructions. This interpretive difficulty becomes a recurring theme across multiple independent descriptions. Different historical sources present conflicting impressions of the same structures, particularly when attempting to describe the size and arrangement of the lower platform. Some accounts emphasize uniformity and order, while others suggest irregularity or incomprehensible scale. These inconsistencies do not necessarily reflect contradiction in observation, but rather the limitations of language and understanding available to each observer. Writers attempting to explain the construction of the site repeatedly encountered limitations in language that made precise description difficult or incomplete. Even when efforts were made to measure or categorize the structure, the resulting descriptions often relied on comparison rather than direct explanation. The lack of suitable terminology highlights how far the monument may have extended beyond the conceptual frameworks of its earliest observers. The vocabulary available in earlier historical periods appears insufficient to fully capture the scale and structural complexity of the platform as it is now understood. This limitation is evident in the way descriptions frequently shift into metaphor or analogy when direct explanation fails. The structure is often defined not by what it is, but by what it is compared to, revealing the absence of a precise descriptive framework. Some accounts focus heavily on comparison, attempting to relate the site to more familiar monuments, yet those comparisons often break down under closer reading. While analogies may provide a temporary reference point, they tend to collapse when confronted with the sheer magnitude and structural uniqueness of the platform. This suggests that observers were reaching for familiar reference systems that could not fully contain what they were witnessing. Descriptions preserved in historical text frequently shift between observation and interpretation, reflecting uncertainty about what exactly was being witnessed. In some passages, the tone is descriptive and grounded in physical detail, while in others it becomes speculative or interpretive. This oscillation indicates that the act of recording the site was itself shaped by uncertainty. Certain chroniclers appear to rely on indirect language, suggesting that the structure exceeded conventional categories of architecture known to them. Rather than offering direct explanations, they often emphasize difficulty, complexity, or incomprehensibility. This rhetorical approach implies that the monument was not simply large, but conceptually difficult to situate within existing knowledge systems. Over time, written references to the site begin to diverge further, with later accounts adding layers of interpretation not present in earlier descriptions. These additions sometimes reflect evolving cultural frameworks rather than direct observation, gradually reshaping how the site was understood in historical memory. The result is a layered record in which observation and interpretation become increasingly intertwined. The absence of consistent terminology across different sources highlights the difficulty historical observers faced when attempting to classify the monument. Without shared descriptive standards, each account develops its own language for expressing scale and structure, leading to fragmented but overlapping impressions. This fragmentation itself becomes evidence of interpretive strain. Some writers appear to have avoided direct explanation altogether, instead emphasizing the difficulty of describing what stood before them. In these cases, the structure is not analyzed so much as acknowledged as resistant to analysis. The act of description becomes a record of limitation rather than clarification. In several accounts, the structure is presented as exceptional, not only in scale, but in the inability of observers to fully articulate its construction. This dual emphasis on magnitude and incomprehensibility reinforces the idea that the site existed at the edge of what could be meaningfully described. It becomes not just an architectural object, but a descriptive challenge. Contradictions between sources suggest that different observers may have focused on different aspects of the same architectural features. While one account may emphasize mass, another may highlight arrangement or proportion, producing divergent interpretations of the same physical reality. These differences reveal how perception itself shaped historical recording. Even when measurements or proportions are attempted, they are often accompanied by uncertainty or approximation rather than precise detail. This lack of precision is not unusual in early historical writing, but in this case, it becomes more significant due to the extraordinary nature of the structure being described. The uncertainty itself becomes part of the record. The cumulative effect of these historical descriptions is a fragmented picture in which certainty about the site's origins remains elusive. Rather than forming a cohesive explanation, the accounts collectively point toward a shared difficulty in fully comprehending what was observed. This fragmentation reinforces the sense that the structure consistently exceeded interpretive boundaries. Later interpretations of earlier accounts often introduce additional assumptions that were not explicitly present in the original descriptions. Over time, these interpretive layers can obscure the initial uncertainty recorded by early observers, replacing ambiguity with retrospective explanation. This process gradually shifts the narrative away from what was actually perceived. The gap between observation and explanation becomes increasingly apparent as more sources are compared across different historical periods. What begins as a direct description eventually transforms into a layered interpretation, revealing how understanding of the site evolved independently of its physical reality. This widening gap highlights the limits of historical reconstruction based solely on textual records. Taken together, the surviving records reflect a consistent pattern of encountering something that resisted clear categorization within known architectural understanding. Across different regions and time periods, observers return to the same difficulty: the inability to fully describe or classify what they were seeing. This consistency suggests that the challenge was not individual misunderstanding, but a shared encounter with something structurally unfamiliar. The persistence of unresolved descriptions in early accounts shifts attention back to the surviving structures themselves as the most reliable record of what was actually built. The stones left behind may be the biggest clue of all. Deep within the quarry system associated with Baalbek, several massive stone forms remain fixed in the bedrock, showing unmistakable evidence of preparation that was never brought to completion. The surrounding limestone bears the imprint of sustained human effort, where extraction lines, rough cuts, and partially shaped surfaces still define what was once an active working landscape. What remains today is not a finished quarry in the traditional sense, but a frozen record of interrupted transformation, where intention is visible but outcome is missing. The site appears less like a place that was abandoned casually, and more like one that stopped mid-process while still structurally active. Carved surfaces on partially separated monoliths reveal that shaping had already advanced to a highly controlled stage before all visible work abruptly stopped. The stone shows consistent levelling along certain planes, indicating that precise planning had already been applied to guide the intended final form. Yet the absence of full detachment creates a visual and structural contradiction, as if the process was carefully executed up to a point that was never crossed. The precision present in these unfinished forms suggests that the work was not exploratory, but systematic and deliberate. Unlike the completed stones transported elsewhere, these formations stand out because their extraction process ends mid-sequence, without the final separation cuts that would normally complete the removal. In a functioning quarry system, the progression from shaping to isolation follows a predictable sequence, but here that sequence appears interrupted at different stages depending on the block. The inconsistency of completion suggests that not all quarrying activity followed the same outcome. Some stones appear nearly free, while others remain deeply integrated into the bedrock with only partial liberation. Tool mark patterns etched into the quarry floor indicate a carefully executed workflow that progresses in clear stages before suddenly discontinuing in select zones. These marks show repetition and refinement, implying sustained labour rather than abandoned experimentation. The abrupt cessation of activity becomes more significant when contrasted with the precision that precedes it, as though the system was functioning normally right up until a specific point of interruption. The presence of repeated tool corrections suggests that adjustments were still being made immediately before work ceased. Exceeding the dimensions of any known transported blocks, several unfinished stones suggest that the quarrying effort had already reached structural limits that were never surpassed. Their scale alone places them beyond what was successfully moved into the monumental platform, raising questions about whether their abandonment reflects physical constraint, logistical decision-making, or something more complex within the construction process itself. These oversized forms remain embedded in the bedrock, as if frozen at the edge of feasibility. Around certain monoliths, incomplete trenches circle the base only partially, leaving clear gaps where final detachment was likely intended but never executed. These gaps interrupt what would otherwise be continuous separation lines, suggesting that the final phase of extraction was anticipated but never completed. The geometry of these trenches implies planning that extended beyond the visible stopping point. The interruption is not random erosion, but a structured halt in a defined mechanical sequence. No finishing edges appear on some of the largest exposed blocks, implying that the extraction process ceased before the stones were fully isolated from the surrounding limestone mass. In complete quarrying sequences, final cuts typically define clean boundaries between stone and bedrock, yet here those defining edges remain absent. The lack of completion leaves the stone physically embedded in a state that preserves the moment of interruption. It is as though the final action was prepared but never executed. Elsewhere in the quarry, consistent cutting methods transition abruptly into untouched rock, marking a sudden interruption in what had been a systematic operation. The shift is not gradual or eroded by time, but sharply defined, as though the working surface encountered an immediate cessation of activity. This contrast creates a visible boundary between effort and absence. The geological continuity of the rock makes the abruptness of this boundary even more striking, since natural processes rarely produce such clean breaks in human-shaped patterns. Positioned awkwardly within partially carved recesses, several stones appear structurally prepared for movement despite never being freed from the bedrock. Their placement suggests that preparation for extraction had reached an advanced stage, where detachment was the only remaining step, yet no evidence indicates that this final phase was ever completed. The stones sit in configurations that resemble readiness rather than abandonment, reinforcing the sense of halted progression rather than failure. Between completed extraction zones and abandoned ones, a sharp contrast emerges that highlights uneven progress across different sections of the quarry. Some areas show fully realized blocks that were successfully removed, while others remain locked in partial transformation. This unevenness suggests that quarry activity was not uniformly halted, but varied across different working zones. The distribution of completion and incompletion forms a pattern that resists simple explanation through gradual decline or erosion. Progression marks along certain quarry faces show repeated refinement of the same surfaces, suggesting continued effort, right up until the point activity ceased. These repeated adjustments indicate that workers were actively improving precision rather than abandoning imperfect results. The sudden end of such refinement becomes more striking when viewed against the consistency of earlier stages. The work appears not to fade, but to stop. On multiple rock walls, separation channels stop short of full depth, leaving structural connections intact where complete detachment would normally be expected. These incomplete channels indicate that final cutting stages were planned but not executed, preserving physical links between the monoliths and the surrounding bedrock. The result is a landscape where intention is visible, but completion is absent. The remaining connections act as physical reminders of unfinished execution rather than structural necessity. Distribution patterns of unfinished monoliths suggest that quarry operations followed a structured plan that was interrupted under specific conditions. The pattern does not resemble random abandonment, but appears to reflect organized activity that stopped in a defined manner. This introduces the possibility that external factors influence the cessation of work. The spatial arrangement of incomplete blocks implies that interruption may have occurred at a system level rather than an isolated one. Significant labor investment is implied by the extent of partial shaping visible on stones that were never fully detached from their base formation. The level of detail present on these unfinished blocks indicates sustained effort over time, rather than brief or experimental attempts. Their incomplete state, therefore, represents not the absence of work, but the interruption of it. The quarry preserves evidence of effort that progressed far beyond initial stages before halting abruptly. Side-by-side comparison of finished and unfinished extraction zones reveals two clearly divergent outcomes within the same quarrying system. One reflects successful completion and transport, while the other preserves only partial execution of identical processes. This divergence highlights that completion was not guaranteed even within a single operational environment. The coexistence of success and interruption within the same geological context deepens the uncertainty surrounding the system as a whole. Repeated tool impressions across unfinished surfaces indicate sustained effort directed toward completion rather than early abandonment. These marks suggest that workers continued refining and adjusting the stone surfaces with the intention of proceeding further. The presence of such continued effort makes the eventual halt more difficult to interpret as simple disengagement. The tools appear to have been actively engaged until the moment activity ceased. Certain quarry sections display near final shaping stages that halt precisely before the final separation cuts would have been made. These near-complete forms suggest that the process was interrupted at a critical threshold, where only minimal remaining work would have been required to finish extraction. The proximity to completion intensifies the uncertainty surrounding the interruption. The stopping point appears almost deliberate in its precision. Spatial clustering of incomplete blocks suggests that quarry operations followed a structured plan that was interrupted under specific conditions. The pattern does not resemble random abandonment, but appears to reflect organized activity that stopped in a defined manner. This introduces the possibility that external factors influenced the cessation of work. The clustering implies that interruption may have occurred in phases rather than as a single event. Taken collectively, these unfinished formations reflect a process that advanced far beyond initial extraction stages before reaching an unresolved stopping point. They preserve a detailed record of effort that was systematically applied yet never fully realized. The quarry thus becomes not only a site of construction, but also a record of interruption. It records both capability and limitation within the same physical space. The spatial arrangement of these unfinished blocks also implies that they were not simply left randomly, but exist within a structured working layout that still reflects operational planning. Their positioning suggests that quarry activity followed an organized sequence of extraction zones that were active simultaneously rather than independently. This reinforces the idea that what is preserved is not disorder, but a system that stopped while still in formation. The scale of the unfinished monoliths continues to challenge modern attempts to fully account for how such material could have been managed with any known engineering method. Baalbek remains a problem. Modern engineering cannot fully solve. Across every line of investigation into Baalbek, the same unresolved structural contradictions continue to surface, regardless of whether the evidence is approached through engineering, archaeology, or historical interpretation. What begins as separate fields of study gradually converges on a shared difficulty, where each discipline reaches a point beyond which its tools no longer produce a complete answer. The structure itself remains physically present, yet its full explanation continues to resist integration into any single coherent framework. This tension becomes more apparent when considering how consistently the same interpretive limits appear across unrelated lines of inquiry. Each discipline approaches the site with different assumptions, yet all encounter a similar boundary where additional detail no longer produces proportional clarity. Instead, the accumulation of data begins to describe the limits of explanation itself, rather than resolving the structure being studied. When modern engineering attempts to model the site as a complete system, the resulting simulations repeatedly struggle to reconcile mass distribution, transport feasibility, and foundational stability within a single coherent framework. Even when advanced computational methods are applied, the behavior of the larger structural elements does not align neatly with expected load-bearing or construction parameters. The system appears stable in reality, yet unstable in replication, creating a gap between observation and reproducibility. That gap persists even when models are adjusted to favour ideal conditions, suggesting that the issue is not related to missing variables, but to how those variables interact when combined at scale. In practice, this means that the system behaves differently, depending on whether it is observed as a whole or reconstructed in parts, with neither approach fully capturing the transition between phases of construction. Material analysis of the stonework, quarry evidence, and platform construction does not converge into a unified explanation, instead producing parallel lines of evidence that resist full alignment with one another. The quarry data suggest one sequence of activity, while the constructed platform suggests another, and the two do not fully resolve into a single chronological or procedural model. Instead of clarity, the comparison produces additional layers of interpretation that remain partially disconnected. Whether viewed through physical remains or historical documentation, each investigative path returns to a shared limitation, where observable data exceeds the boundaries of conventional construction logic. This does not imply absence of evidence, but rather an excess of fragmented evidence that does not naturally resolve into a single explanatory structure. The result is a system where information is abundant, yet synthesis remains incomplete. Engineering reconstructions developed to replicate the scale of the platform consistently encounter breakdowns at different stages of the process, despite variations in method or technological assumption. Some models fail at transport simulation, while others collapse under load distribution analysis or terrain friction constraints. Each attempt isolates a different weakness, but none succeed in resolving the full sequence of required operations. Even when simplified models are applied to isolate individual aspects of the structure, the combined weight, scale, and positioning of the stones continue to exceed workable parameters. This suggests that the challenge is not confined to a single engineering step, but distributed across multiple interdependent stages that cannot easily be separated. The problem persists even when complexity is reduced rather than expanded. This reversal is significant because it contradicts the expectation that simplification should improve interpretability. Instead, reducing the system isolates the same unresolved interactions in sharper relief, making the boundaries of the problem more visible but not more solvable. The structure resists not complexity itself, but the act of decomposition into independently explainable parts. Historical accounts, when placed alongside archaeological findings, do not resolve the contradictions but instead highlight the gap between observation and explanation across different time periods. Written descriptions often emphasize scale and uncertainty, while physical evidence emphasizes precision and execution. The two forms of record do not directly contradict each other, yet they fail to merge into a unified narrative. Attempts to treat the site as a single-phase construction project introduce inconsistencies that reappear in every known layer of analysis, regardless of discipline. The assumption of linear development struggles against evidence suggesting multiple phases of activity, interruption, or redesign. Each explanatory model introduces new tensions that were not resolved by previous interpretations. The persistence of extremely large monolithic elements within the platform system creates a structural condition that does not align with expected outcomes in comparable ancient construction contexts. These elements are not marginal features but central components of the structure, integrated in a way that suggests deliberate and highly controlled placement. Their presence raises questions that extend beyond simple construction capability. Each attempt to isolate a single explanatory factor, whether transport method, labour force, or chronology, fails to account for the system as a whole. When examined individually, each factor appears plausible within a limited scope, but none can fully explain the complete sequence of quarrying, movement, and placement. The problem persists precisely because it cannot be reduced to a single variable. In comparative studies of ancient monumental architecture, no other site exhibits the same combination of scale, precision, and unresolved structural behaviour seen at Baalbek. While other ancient constructions demonstrate impressive engineering, they typically remain explainable within known historical or technological frameworks. This site continues to resist that categorization even under extended comparison. The deeper the investigation progresses, the more each category of evidence appears to function independently, rather than contributing to a unified historical reconstruction. Quarry evidence, structural analysis, and historical record each form coherent internal narratives, yet they do not fully integrate. The separation between these narratives becomes more apparent as the detail increases. Even the most conservative interpretations of the available data cannot fully eliminate the structural anomalies present in both the quarry and the constructed platform. These anomalies are not isolated irregularities but recurring features that appear across multiple stages of analysis. Their persistence suggests that they are integral to the system rather than incidental to it. At the point where engineering explanation would normally stabilize into consensus, the available evidence instead expands into additional layers of uncertainty. Each resolved question appears to generate new conditions that require further explanation. The expectation of convergence is repeatedly replaced by continued divergence. The accumulated findings across all previous chapters do not resolve into closure, but instead reinforce a persistent gap between what is physically present and what can be fully explained. That gap does not diminish with additional study, but remains consistent across different investigative approaches. It becomes a defining characteristic of the site itself rather than a temporary limitation of research. The unresolved complexity of the Baalbek platform continues to sit at the edge of modern understanding, where every new explanation appears to approach the problem without ever fully reaching it.